Okay, so we did start with 3D rigid rotor. So this test begins there. There's a bit of a weird split between test 2 and where we begin test 3. And is everything, of course, at this point, hopefully you're sick to death of this. You know that kinetic energy is quite simple, a double derivative in space, not time, which would be different than what you would have had in physics mechanics. And when we convert that to that's 3D. When we convert it to 3D spherical coordinates, it gets funky. Now actually, I'm kind of used to this at this point. It doesn't scare me as much as it did before class, and I do this every year. But tell you what, now wait a second. Let me write out the Hamiltonian, and just give me a second, because then I'm going to act on a wave function. So don't write it out yet, because I want you to give yourself some room. So again, what I'm doing is I am writing the Hamiltonian, but I'm going to apply a wave function to it in a minute. So give yourself a little bit of room, or maybe better yet, just wait for me to just write this out, and then I'm going to apply the wave function. And again, what you might do is you may not give yourself enough room to write the wave function, and then you're like, well, wait a minute, what's what? And your notes are kind of crappy, and I don't want that. Okay, so again, I remember the first time I wrote this out in class, and always a little afraid that you folks may have looked at that and said, oh my dear God, what the heck? So there you go, right? Now, what I want to do is I'm going to apply a wave function to it, and when I do so, I know that these walls capture, like this is a theta wall, so it captures the theta wave function. Don't forget that the reason that this term just isn't cosine, we saw some of you do that on the homework, is because you don't know what this is yet. If this is a constant, then sure, you can turn that to a cosine. If this is not, then you can't, and you should know that. Now, the wall does not catch a phi wave function, so that passes right on through. This phi wall catches the phi wave function, but it doesn't catch the theta wave function. Okay, now if I've acted on the operator with the wave function, you know that, well, where's my energy? Well, my energy better be right out here, and here are my wave functions. There we go. So in the eigenvalue equation, just like you're used to. Got to be careful, m's are now masses, because m is now a quantum number for the 2D rigid rotor. Don't worry about that, that's not on the test. Let's see. Now what we got to do is we want to turn this into a separable wave function. You know that the process of separation, which I was somewhat obsessed with, but just heads up, I did not put that on the test. So I've acted on it, but with the wave function, then I divide it on the left by 1 over a wave function. And this allows me to show separability, and again, that's very important for solving it. Although that's the thing, I kind of hate to emphasize this so much, because what we do is when we separate it, we just give it to a mathematician. Hey, mathematician from the 1700s, solve it and bring it back to me, and that's how it works. Sometimes on previous tests, I created a little Hamiltonian and asked you to show separability. I did not do that on this test. But I may do so on the final. That's why I'm saying that, and that's why I'm doing this. Okay, so now I'm going to do the division on the left, and what we end up with, I'm going to do this division on the left, and I'm also going to do a lot of constant rearrangements, like multiplying by sine squared to get rid of this theta and this phi. This is not separable, so I'm going to get rid of this theta from this phi, because I got to, by multiplying by sine squared. I'm going to multiply by these guys as well, bring them all over here. So just note that I'm doing a lot of algebraic manipulation. I'm not going to write all that down. You can handle algebra. So here's the division by the wave function on the left. Again, I've gotten rid of my sine squared theta by multiplying it, so you don't see it yet. The theta wave function, of course, is stuck by the wall. When I multiply this term by sine theta, I end up with a sine theta on top. Multiplied by sine squared theta, I got a sine theta on top. I've also still divided by the wave function on the left side, so there that is. Remember the phi has been eliminated by that separation process. Then the rest of it goes the same because the wall doesn't allow the theta to, that it's all the same. Blah, 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 blah. Anyway, okay, so then what? Then I'm going to bring over the constants, 2ie over h bar squared. So here's my, here's 2I h bar. Of course, it's flipped over. It's a minus, but I brought it over on the left side, so now it's a plus. Oh, don't forget my sine squared. There we go. And that's now equal to 0. I do have you work on this, by the way. I'm just straight up tell you. I set this up and I have you apply a wave function. Thank me later for telling you that. It's a bit of a biz knocker, and it's one of the early questions, which normally are the easier ones. Normally I would say that for a derivation. I'm doing it because, for one, I gave you like a real simple example, and number two, you should be like way good at this by now. And you know the answer. Because this is the answer, right? This has got to equal 0. So I have you do one of these. You can choose to do it or not, and you know the answer. So and it just shows your confidence at doing all the mathematical stuff that we're supposed to do. Okay, you know that this is miniature Schrodinger equation, Schrodinger equation number 1, and we assume that the 2D rigid rotor is valid. And this is Schrodinger equation, mini Schrodinger equation number 2. If we assume that the rigid rotor is still valid, this is equal to minus m squared, and then therefore this is equal to plus m squared. Notice we also see the funneling of energy into one of the sub-Schrodinger equations. Again, we've seen all this before. A bunch of constants, but not too bad, especially because we get the answers. We get the answers from a 17th century mathematician with that tarnish that shows up in class if you watch the videos, which half of you are doing apparently. Okay, so again, we go back in time and ask a 17th century mathematician what the answers are. They solve these things just for the hell of it, because they could, but why does humanity do anything? We know that an L of 0, M of 0, the wave function is a constant, and actually that kind of makes sense because plug in a constant and all the derivatives are 0, and I actually forgot why that works, but anyway, it works though. That's not the one I gave you though, because that's too simple. You know that the L and M quantum numbers feed off each other. So we'll talk about degeneracies. There's a degeneracy in the quantum number. I'll write down the energy in a minute. And the number of degeneracies is due to the play of M and L off each other, where L is whatever, right? So L of 1 is S-like. 2 is P-like. Yada, yada, yada. M is minus L plus 1, dot, 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 0, dot, 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 L. So there are 2L plus 1 degeneracies. And I've gotten completely distracted from writing down the wave functions here. Sorry, I'll do that in a second. There's always h bar squared is in freaking everything. So here's a little factoid. When you're looking at equations for things, like I go to a talk on quantum fluid flow, I don't know, quantum kitty cats. And I see an h bar, that's a quantum mechanical result. If it's classical, there's no h bar. It's just kind of a neat thing that happens. Anyway, sorry, I got distracted in writing these wave functions. Yeah, so here they are. You know that these things have a way of ballooning, getting nutty real quick. And there's patterns. If you look out on Google, there's tables of spherical harmonics. These are called spherical harmonics. They get this little symbology here. You actually will notice that there's a pattern to these. Anyway, that's not important for this class. I just think that's kind of neat. And here, of course, is the 2D rigid rotor, and yada, 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 yada. So here we have a S state, n equals, S state, wait a minute, have I done this right? Yeah, S state, P state, there's 3 P states, so yeah, so here's our degeneracies. So the important thing is they only depend on L, but then there's 2L plus 1 degeneracies, right? So there's only one S state. 2L plus 1 when L is 0 is 1. That means that there's only one state. It's easy, non-degenerate. Now I've got, when we went back in time and got the answers from the 17th century mathematician, the guy said, well, if you plug in L of 1, I actually have 3 answers, and it depends on this M subquantum number. Oh, but all the energies are the same, so therefore you got a triple degeneracy. Remember, that only happens because we live in multiple dimensions. If when we were doing all our 1D, remember a while ago, 1D simple problems, a little particle in a 1D track, you never had a degeneracy. It was impossible. Once we started doing 2D and 3D, degeneracy started showing up. Anyway, I just thought that was kind of neat. All right, well, so I think I've told you tons about what I'm going to do. Let me cast this into a slightly different form. J squared over 2I. And remember that J is, actually I can, yeah, J squared over 2I, J squared over 2I. We call J is the traditional physics mechanics angular momentum. Angular momentum is J squared over 2I. Just like P squared over 2A, I'm at J squared over 2I. It's nice, that's very homologous, and I like that. It makes me more comfortable. Now I can also figure out things like J itself is, now this is silly, by the way. This is just the square root of L times L plus 1, H bar. I always say, it's kind of fascinating to me, when we did 2D rigid rotor, J was just M H bar, and I like that because it reminded me of just a particle on a track where the momentum was just K H bar. For 2D rigid rotor, it was MH bar. And then when we go to 3D, not only do we get more degeneracies, but we get this little complication. It's not LH bar, it's L times square root of L times L plus 1 H bar. I don't know what to make of that. It is what it is, but it kind of makes it harder to see how the 2D and 3D aren't that different, right? Because anyway, it is what it is. I just thought that's kind of neat. Let's see, now what do I want to say? Oh, yeah. So now this part's definitely on the test. When I started talking a little bit more about angular momentum, I mentioned to you that you had a little homework where you found that you can know the angular momentum and the z component, and that means that there is no uncertainty relationship existing between them. And I didn't make much of this. Sometimes I do in some classes, sometimes I don't in other classes, and it just happened that I didn't. I had you look at some of those operators. They were a little complicated because angle stuff is complicated. But you found that this was the case, but where it got a little bit more interesting was that if you did z and x or y, you found that there was an uncertainty principle, right? The commutator, these are commutators. So they, this is just what they come out to be. Go figure why it is what it is. Do the math, it is what it is. You did do the math and you saw this behavior. And there's a consequence. And I'm going to bring that up, the world's inventor laser guy will bring that up on Monday. This is actually how Fourier transform NMR works. And again, I'll talk about that on Monday. I just want to tell you that it's kind of neat. I hope you think it's neat. What happens is, now remember that if I'm spinning my arm around, if I'm spinning my cat Charlie who's throwing up again, if I'm spinning her around, the J is the axle, right? So it's easy to remember that, right? So if a JZ of 0, so I'm spinning, so I've definitely got a J. The Z component is 0 because I'm in the plane. All right, now if I tilt the cat up, then the axle is now kind of at 45 degrees and whatnot. So then there's a projection onto the z-axis. Now let me draw that, because I know that was a handful. Let me do the x and y axis. So now again, remember that this is the j axis. That is where the rotor is pointing. The actual motion is orthogonal to that. It's just a nice convenience that angular momentum is a vector. I can express two-dimensional rotation with a one-dimensional vector. That's just kind of convenient. Okay, so there you go. Now, I've got a projection onto the z-axis, which is 0. X and y. I've got a projection onto the z-axis that's 0. So I know the total angular momentum. That is, of course, the length of this vector is L, square root of L plus 1. Sorry. Square root of the whole thing. Okay, so that's the length of the vector. That's the j. The z projection is 0 because it's in it bisects the z. And I'm drawing this as a plate because I can't know the x and y component. So what happens is, if I get a quantum object and I get it rotating like this, and you can do this with fancy spectroscopy, and if you're doing NMR, you do this with fancy radio signals, by the way, Monday. But what happens is, right now I have perfect information. If this is the thing that's spinning, I know exactly where it is, but this uncertainty principle says that I can't. So what happens is I start doing this, right? So the axle is somewhere in the x and y plane, but I don't know exactly where. It's in the x and y plane because I know that the z component is 0, but I don't know exactly which way it's pointed. So what happens is, if you create a quantum system with the axle well defined, it starts rotating on its own, which again that's how NMR works, and we'll see that on Monday. Okay, so now that's the z component. Now you know that if we have an angular momentum, let's do like a p state. If we do a p state, then you know that there can be a greater projection into the z-axis. So I'm drawing that here, trying to make it look nice. There we go. Okay, so I can have this situation. There's a corresponding negative deal as well. So again, I'm not trying to make this look hideous, but this is the best I can do. Okay, so this would be for a what am I drawing here? I'm obviously drawing an L equals 1. I've drawn an M equals 0, M equals minus 1, and then M equals plus 1. And that means that this is as h bar of momentum. So anyway, so if I'm tilted like this, then I'm like doing like this. So anyway, so that's how that looks. So anyway, if you see a figure like this, the reason that they're cones is because of an uncertainty principle between the x and y of the components, x and y angular momentum components. Let's see, next part. So that was really all I have to say about angular momentum. Remember that spin is a type of angular momentum. I'm jumping a little bit ahead here. Spin, which I never brought up. We got J, we got L, we got M, and that was fine and good because I can wave my arms around like a maniac and you actually know what I mean. But later when we got to multi-electron atoms, we started talking about spin. And spin is a dynamic that we do not know what it is, but it behaves just like angular momentum. It's the weirdest thing. No one truly understands this, not even today. We have no way of probing it or observing it other than just it does seem to behave like angular momentum. So spin type of angular momentum has, instead of the j squared, we have an s squared. I didn't mention this before, by the way. Actually, I think I did at one point, but you probably were like, what the heck? We have, of course, if this is like, well, what the heck is that? It's the same thing as L. It's just that it's an angular, it's a type of motion that we don't know what it is. And you know that the Z components are plus or minus 1/2 h bar. That's what we would call alpha or beta. Also note that the wave functions are literally symbols. We can't give them a mathematical form. We don't know what's happening. We don't know what's turning. If we don't know what's turning, how can we say that it's e to the theta or e to the phi? We can't do that. We don't know what's happening. We just give them like prints. It's like an impronounceable symbol. So anyway, all right, well, I'm kind of jumping ahead. I just wanted to talk about other types of angular momentum when I'm talking about angular momentum, but let me go on to the hydrogen atom Hamiltonian. Ugh, I can't talk. Okay, so I'm going to write this out in a separated way. I can't redo all of that. There was about 1.5 lecture where I introduced the Hamiltonian, and I did separation, and then I threw the wave function at you, and then we looked at the energy. So that was really about a 2-lecture process. So I can't remotely do that. I'm just going to point out that when we were doing the whole separation dealy, the angular momentum just kind of fell out. We claimed separability, although that's a little tenuous. And so we just assumed that the rotation part, the rotation of the electron was something that we understood, but R was no longer fixed. And so that created a split off Schrodinger equation. So instead of 2 Schrodinger equations for theta and phi, we had a third with R, and the energy wanted to go into that one. And that left us with this. And I'm going to write this in the separated form. And you can tell because I'm writing 1 over the wave function on the left. And again, this is a math-friendly version, although, as I've said a zillion times, we're not actually solving this. When I took this class, we actually did take an entire week to look at the solution as performed by a mathematician. And sorry, that's a 2 over R. That's not a derivative sign. That's a derivative sign. I accentuated it there. We actually did see how a mathematician solves this. And I don't know, I just didn't get much out of it. It's just a bunch of derivation. And so I didn't do that with you folks because I was like, what the heck is the point? Do you believe that this is a partial differential equation? Do you believe it can be solved? Hopefully, yes. And so I think that was enough. I might be writing too small here. There you go. And now again, remember I was saying that there's a little weirdness with separability between the angular momentum, the angle pit, and the R bits, and you're seeing that, a little bit of that right there. So remember, this is like the rotational energy filtering down to the kinetic, to the radial part, and the radial part managed to have the energy fall into it. Again, I'm writing this in a separated way. Okay, so there you go. Now, a couple of tricks I did. Now, I didn't do this on your test, but I've done it on others, and so I'm leaving at the caveat that I made them put it on the final, although I did not put this on this test. Just so you know that, we've done this a couple times. You can turn operators into other operators. I like this one. It's a little easier. And of course, you can see how this turns into that. This turns into that when you apply a dummy wave function, and then you do a product rule, and then you can see that these are the same thing. Maybe on the final. Didn't put it on this one. Anyway. Okay, so again, here is the full-blown mathematical yada, yada, yada. The interesting thing is that, okay, kinetic energy, this is all the kinetic energy. So this is all the potential energy, and that ought to be the total. That makes sense. This is all positive. Don't let that minus sign fool you. Remember that derivatives have a tendency to bring up minus signs. So this is positive, and this is where we get kind of funky. The potential energy, which is purely Coulombic, is only negative, and it technically drops off to minus infinity. And that's ultimately why we get, here, what do I want to tell you? The energy here, I'll write it like this. I normally don't do this. The energy ends up being negative, which is odd. It's a very odd thing. It doesn't really matter, but I'm just saying. All the other energies we always calculated were positive, but energy is relative. I don't know if you remember, but last semester I said, I don't know if there is such a thing as energy. There's only changes of energy. So whether I say that it's plus or minus is actually irrelevant. Okay, so we get this giant thing for energy. Now again, you get this thing, you ask a mathematician friend to solve it. They give you wave functions, they give you energies. Here, let's look at the energies. I've just said about everything I can think of about the energy. It's minus 13.6 eV. And in terms of, if I shine light on that to rip the electron off the proton, I would have to use, again, I don't know that you have enough experience with spectroscopy, twice your age, but 91 nanometer light is unbelievably powerful, all right? I'll tell you a little bit about how you generate that kind of, we can actually generate those wavelengths of light. Question?
E in these equations are always just referring to the number?
Actually, no, I think I mentioned that once and I screwed up. That's the electrostatic charge.
Okay, so negative.
Whatever the number of coulombs of an electron is in SI units. Yeah. These are always 10 to the minus 19 or 34 or something. So it's a very small number of coulombs, and that's because you can see the Coulomb's law, the 4 pi E naught deal showing up here. So that needs to be balanced by some electrostatic charge, not exp0. I think I told you that once. Sorry, I screwed that up. It's electrostatic charge in coulombs. Is that a question?
So I think your minus sign is there because the electrostatic charge on the electron is negative.
No. It's because potential energy is purely negative.
Right. For the electron.
Now, so remember, this is negative because I've got a positive nucleus and a negative electron, and Coulomb's law then has charge 1 times charge 2, and there's a minus sign. Right. So the potential energy ends up being negative. The kinetic energy ends up like creating these rungs. Think of it this way. Think of rungs being created in the potential energy surface, and these rungs are like the quantum states. And since there's this 1 over n squared, they get closer and closer together. Now I can't really draw them. And so this is how you want to think of that. We've got this n equals 1. So when we solve this, we end up with a new quantum number, which is n, which dictates the energy. That also introduces degeneracies because the energy only has an n in it. Our new quantum number, the L and M quantum numbers don't play a part. That means that we have degeneracies, and I'll write those down here in a second. Anyway, we're okay. Any other questions? All right, so let me move on. Those are the energies, and we can verify that. We can make 91 nanometer light. We can make 1 nanometer light, by the way, with the synchrotron, which is what I'm going to go talk about on Monday, which is really kind of cool. Some of you may end up working at Argonne National Lab. Some of our students, our grad students, sometimes they end up doing research stints at Argonne. Sometimes they do their whole career at Argonne National Lab. It's a really weird thing because they do research, but they're not a school, so they don't have grad students. Trust me, that is unbelievably weird. They have to pay postdocs to do the work of grad students, and that just is a problem for them. But anyway, we solve that problem by bringing them grad students sometimes, so they're really happy to work with us. Sorry, I don't know why I'm talking about that anyway. Okay, so I've got the energies from the radial. I also get the wave functions. The wave functions are always, we have a normalization. Again, we never really need to worry about that. We get this R to the L showing up. We get some kind of connector. And the connector often generates nodes, which generates kinetic energy. You know that you always see a node. When you go up a quantum level, there's always a node showing up, an extra node. Go up another one, you got 2 nodes. E to minus R over A naught. Now, sometimes it's R over A naught, sometimes it's R over 2A naught, sometimes it's R over 3A naught. That's just because the wave functions get bigger and bigger as you go up the n ladder. They get further away from the nucleus. I talked a little bit about that once. It's not a big deal. Okay, now this guy is important. It's all about the angular part. This prevents, this is for, it only shows up when you have P and D functions. And what it does is it prevents the electron from doing this, right? So the electron is spinning. Now, it only spins if I have P's and D's, right, and F's. If it happens to wander too close to the nucleus, just like a skater pirouetting, it goes faster, right? It goes faster if it gets too close. Well, due to our mathematics, if you get 1 over 0, you got a major problem. And so if you don't have this, if the electron got too close to the nucleus while it was spinning, it would spin at the faster than the speed of light with infinite energy and kabammo, right, into the world. So that prevents that from happening. Connectors can bring up nodes. This kills it off. Kills off. The electron can't go away, can't just traverse through space for infinity from the nucleus. So this basically says no matter what's going on with the rotation or nodes, eventually the wave function tapers off to nothing if you look far enough. So anyway, you almost always see this. Whenever I look at more complex wave functions, I always see this. Okay, next thing real quick. This is a very graphical test. I have tons and tons of graphs on it. So you should know that without this, with this R of L, when L is 0, it's not there. So you get wave functions that look like this, and this is, of course, is a 1s. And I can tell it's a 1s because there's no node. There's one node, so that makes this a 2s. Again, the wave function can approach, has some finite value at r equals 0, because you don't have to worry about it spinning out of control when it gets close to the nucleus. However, you do have to worry about the electron touching the nucleus, which would also cause a cataclysmic explosion of the entire universe, which hasn't happened, not yet. And so the reason that that doesn't happen is, remember that Jacobians, for when you do integration, have an r squared in them. So if you plot r squared, what we call a radial distribution function, then the 1s actually looks like this. Remember that this is actually a better way to plot things. It's more realistic. This takes into account the fact that this lives in 3D, not 1D. I've drawn this one-dimensional with one x-axis. I really needed to draw 3, but I can't. So this is actually better. And it shows that actually the wave function never touches the nucleus. It's just an infinitely small point and it never finds it. So this is a good thing, right? That prevents the world from ending. Okay, let me do the P's and D's. Okay, so a 2P, because of this guy, it will actually not, it will be 0 at 0. And so that's how you can tell a P different from an S. So here's a 2P. Notice that it has no nodes because it's the first of its kind. The first P is the first P guy to show up. So there's no nodes. And that means if I saw a 3P, I'm looking at my notes because I want to make sure I draw it right. I know that's a 3P because it has a node. It's the second of its kind. Okay, right now you can tell S's and P's, and guess what's on the test, right? That's why I'm talking about it. Okay, but let me point out something. This is kind of cool. Technically, a 3D is the first of its kind. This is a 3D. And look at that, no nodes, right? It's the first of its kind. So be careful. A 2P and a 3D are actually really freaking hard to tell apart because they both are 0 zeros. Again, because so they don't spin themselves to death, and they have no nodes. So they actually are kind of hard to tell apart. If I plot two of them right next to each other, good luck figuring out which one's which. Except that you would have a bit more of a cusp here because you have an r squared term versus an r term that you have here. It also is occurs at longer distances because it has it's an n equals 3 as opposed to n equals 2. And I think I mentioned this in class once, but the average R is proportional to, I think it's n squared. I mentioned that in the second hour on Friday. So anyway, I kind of got fascinated that the 3D and the 2P are, actually, they'd be really hard to tell apart. Okay, and that was, yeah, really all I had about these deals. The next thing was, so we looked at the Hamiltonian, we looked at the wave functions, we looked at the energies, and that's really all you can really do with it, except now you can also, you can do things like take the wave functions and figure out turning points, and I think you did that on one of your homeworks, and you can, what else? Oh, we did spectroscopy, which makes it back to this test. Okay. And let's see, what do I want to see about spectroscopy? Spectroscopy is all, we only really care about, when we do spectroscopy, it's all about this. It's all about the difference dipole. A difference dipole. And I'm just going to write this, I guess I have to put two integrals, and that's not, and I'm ignoring the fact that I've got 3 dimensions within those 2 integrals, because I've got, no, wait a minute, no, that's not right, that's not right. It's the same, am I doing this right? It would be, yeah, I'm talking about a single atom, so I need to just do one integral. That one integral represents r theta and phi, by the way. Sorry, don't even worry about this, it's way easy on the test. Now, there's a final state. Now, since that's on the left of this thing that this average value equation, since it's on the left, it gets a little star. That doesn't matter when it comes to hydrogen atom. There's no letter I. Sorry, there actually is, depending on the rotational state. Anyway, so all you want to know is it 0 or not 0? And this is how we get selection rules. Right, so that's the origin of selection rules. And let's see, what do I want to say about this? What is kind of funky about this is that you're used to doing average value questions where these are the same state. So like, what's the average kinetic energy of a 1s electron? What I would do is I would have the kinetic energy operator, and I'd have the 1s wave function here and here, and the 1s wave function is not complex, so these would be the same thing. And that's how you would calculate that. But this is different. Because you have to have a different state as the final state, because you absorb energy, it's just a little weird, so look out for that. This is some initial state, we'll make it a ground state, and this will be a final state, which will be whatever you want it to be. And the reason you're doing that is you just want to see whether it's 0 or not. If it's 0, it doesn't show up in your spectra. If it's not 0, it does show up in your spectra. This is how we understand spectra. So anyway, just wanted to point that out. Now, this is the dipole operator. And it mimics light. Its job is basically to mimic light. Because, I mean, light's an electric field, and electric fields monkey with dipoles. They interact with each other. And that's a very strong interaction. And that's why we just think about light interacting via dipoles. You don't really have to do it that way. And the dipole operator is minus Coulomb charge times x, y, or z, depending on the polarization of light. Now you could also do, note that I'm not doing circularly polarized light. Light does come in circularly polarized form, but if you drive it through a plane polarizer, you can make things x, y, or z polarized. Now you know that for z polarized light, z is r cos theta. And so when you plug that into here, you get selection rules. Remember I said that when it comes to spectroscopy in atoms, we're always fixated on the radial. The radial seems so important because it gives us energy. The damnedest thing is, when it comes to spectroscopy, that's actually never the hard part. Those are usually easy integrals. But you get an angle part too. And the angle part ends up being where you figure out your selection rules. And in the case of hydrogen, you get a delta L of plus or minus 1. And there's an M selection rule as well, but don't worry about that. That's a really fine detail, and I I think I know it off the top of my head, but I don't really care. And remember, one way to know that you've got to worry about the angles is that technically this is a spherical harmonic of L equals 1, Z happens to be M equals 0. And note that this also preserves, this captures the angular momentum of light. It just works out that way. It's not designed to do that, it just does it, but it should because that's right. And anyway, I find that kind of synergy kind of remarkable. Okay, now the next thing is multi-electron, and I have a fairly large number of multi-electron bits, and I know I'm not giving this enough time, but then again, we just covered it. You know, I try to bias my reviews on stuff that we haven't covered in a while because you've maybe forgotten about it. But look, heads up, multi-electron is about, not half the test, a little under half, maybe 40%. So just recall that when you're studying. But then again, obviously that's the part you just turned into homework, right? So, and I do have you look at Slater determinants, by the way, that's on there. Okay, so remember that when it comes to a multi-electron deal, you end up with two kinetic energies, and I'm writing the radial one because that determines the energy. Also for two electrons, you get the same thing twice, basically. You get your hydrogen Hamiltonian twice. There's our electrons interacting with protons, but the electrons interact with each other, and that's just a problem that, you know, I mean, it's there. I mean, there's nothing you can do about it. It's also inseparable. And this is where, again, now we're talking about like graduate level stuff at this point. Graduate students work on this problem. That the radial wave function is not separable into a 1 times 2 form. So R2. You can't do that, but we do it anyway. Because we don't have any idea what else to do. So go to grad school, become a theoretician, and you work on this problem. And it's kind of interesting to see what you come up with. The other thing is that you also have to worry about, and let's talk about degeneracies, you have to worry about this kind of stuff. You've got to not do that. If you do that, your wave function better be 0. I don't have a proof for this. This is an is. You can't have two electrons in the same state at the same time. If you draw this, you better get a wave function of 0. If you do this, you're cool. If you do this, that's cool. Notice that I was careful to make this a optical transition. That's cool. And so is this. That's singlet. The other one's triplet. Those wave functions are not 0. Okay. Now the way you go about that is you write. The way to fix this is to make sure that you see this property. That if you switch the order of labels of the electrons, you have to pick up a minus sign. And again, I can't tell you that's like filling a hole or when a trout goes up a stream. It's literally erasing labels on some writing, which is physically meaningless, yet it must be true that it comes out that way because that keeps your wave functions behaving correctly in terms of you can or can't do. Note that, let's see, because of that, the wave functions end up becoming determinants. So folks, I know I'm out of time. Know this, know your determinants, know your triplet wave functions go like alpha, beta minus, sorry, that's a singlet, beta, alpha, a triplet. I know I'm using a little bit different terminology. Triplets have three different ones, and then the weird one, alpha, beta, plus beta, alpha. That's really weird But those are your three triplets, that's your single singlet. Remember that they can be cast as a determinant form, and that when you plug the wave function to that giant Hamiltonian, as usual, I've just talked about wave functions, let me talk about energy. You get a kinetic energy, you get the Coulomb of the electrons and protons, and then you get this weird exchange term. This really, really weird exchange term, which is plus for singlet and minus for triplet. And that's why this triplet wave function is actually, this singlet wave function is higher in energy than this triplet. Recall that, because I'm out of time, recall that the way singlets and triplets convert between each other is through spin-orbit coupling. Spin-orbit coupling is a part of the Hamiltonian. I wrote out this Hamiltonian. I could add more stuff. I could add gravity to this. I could add spin-orbit coupling. I could add dark energy. There's other energy terms that I could be adding to this. In the case of spin-orbit coupling, it's L dot S. And a consequence of this is that you can't write the wave function with separate spin and space components. You can't do that, but we do it anyway. So you can imagine that I might add terms to this Hamiltonian and ask you to analyze the result. What you're looking for is, can it be separated or not, and what's the effect on the wave function? Seriously, that should be enough to answer. So I just, as usual,